Hello, you're welcome to my channel. It's another time for physics tutorials, and today we'll be doing some kind of continuation from where we stopped on electric field. Okay, here is the question. It says in a rectangular coordinate system, a charge of 25 times 10 raised by minus 9 coulomb is placed at the origin of coordinates, and a charge of minus 25 times 10 raised by minus 9 coulomb is placed at the point x equal to 5 meter and y equal to 0 meter. Determine column A, the force between the charges, stating whether it is attractive or repulsive, and the electric field intensity at the point x equal to 2.5 meter and y equal to 0 meter. So we'll go with the solution now. Now, looking at the question, just like we normally solve physics, we take down the parameters we are given. In a rectangular coordinate, a charge of this. So we have charge Q, take it down as Q, is given as 25 times 10 raised to power minus 9 coulomb. That's a positive charge. Is placed at the origin of coordinates. So this one is placed at the origin of coordinates. That is, it's placed at a 0, 0 mark. Now, then you have a charge of minus 25 times 10 raised to power minus 9 coulomb. That's let's call this one Q1 then, and call this one Q2. This time around, this is a negative charge. Minus 25 times 10 raised to power minus 9 coulomb. They said this one is placed at x5, x as 5, and y as 0. So good and fine, we can easily draw a linear expression for this. If you say something that's placed at the origin, let's imagine that the origin is this point. Let's imagine that this point is the origin. Definitely negative x will go towards this side and positive x will go towards this side, towards the right. So now, if you move 5 meters towards the right, you have the other charge here. The Q1 is here. You have the other charge here, Q2. This distance between them is 5 meter because that's in the x. That's x5, 0. You understand? We didn't move. We are not moving up in any of these cases. So y is 0 here, y is 0 here. We didn't move up, and we only moved linear motion. That's x from 0 to x as 5. This was 0, 0. That is, we didn't make any horizontal or vertical motion, in the sense that we didn't move up or down. So, making progress, we have discovered that just by drawing properly, we have the distance between the two charges is 5 meter. So we can record our R as 5 meter. So now, the first part of the question said you should find the force between the charges, stating whether it is attractive or repulsive. So the formula we'll be using for determining the force is F, given as K Q1 Q2 over R square. So definitely, I think you must have seen something similar to this in my last class. This is the formula for the Coulombic force. So definitely we have Q1 already as 25 times 10 raised to power minus 9 coulomb. We have Q2 as minus 25 times 10 raised to power minus 9 coulomb. Definitely. So the value for K, we know it as 9 times 10 raised to power 9. Then you have R, the distance, which we determined 5 meter. Now we can easily place everything into the formula. 9 times 10 raised to power 9 times 25 times 10 raised to power minus 9 times minus 25 times 10 raised to power minus 9. All over R square, 5 square. Once you use your calculator properly here, you discover that your answer is going to be 2 minus 2.25 times 10 raised to power minus 7 Newton. Of course, when we are making reference to force, when we are calculating force, ordinarily, as a physicist, I will tell you that you definitely add this as a negative charge here. But when you are to implement this, you remember from my last class, it's good I explained this very definitely. You had me writing a formula like that made these charges to take a modular form. Let me just say it as modulus, like you put them in the form of modulus. That is, you make every negative sign a positive. So what I'm trying to say is that you should have written it like this: k q1 q2 over r square. When you get to this answer, some people use the notion of, okay, since it's a negative sign, this negative sign, you can say, okay, since it's a negative sign, you can therefore call it an attractive force. But I want to tell you that if you keep doing it that way, you are going to defile some rules of physics. Why not just go with the original formula, k, the modular form? So people generally know this formula, but it will affect your explanation of the force. And now look at how we go about this. We impute everything. This time around, since it's modular, definitely 25 is positive. Then this one that was supposed to be negative will still be written as positive. 25 times 10 raised to the power minus 9 all over 5 square. So this time around, we're writing our force as 2.25 times 10 raised to the power minus 7 Newton. So the basis of our determining which type of force is this is not the sign here. Now, generally, some people or textbooks will say, they will say, since it's a negative sign here, then definitely it's going to be an attractive force. But I'm going to tell you that now, if we use the normal formula, we're going to get a positive. So the basis for your saying it's an attractive force or a positive force is you go back to the first law of Coulomb that says, okay, if this charge is positive and this charge is negative, definitely, unlike charges, definitely will attract. This is a positive charge and this is a negative charge. So definitely they will attract. So any force between them, you understand, is going to be what? An attractive force. So this is an attractive force, which is an attractive force. So the basis of our saying it's an attractive force is not because of the sign here, but because of the fact that when we look at the two charges, one is positive, one is negative, definitely by the first law of Coulomb, unlike charges attract, like charges repel. Assuming both were positive, definitely it will be a repulsive force. So thank you. That is for part A. Now let's go to part B. For part B, he said we should talk about the electric field intensity at the point X at this point. So we've settled part A and we've determined that it's an attractive force. He said the electric field intensity at the point at this point. So now this is the original diagram we had. So let's introduce that point in between. Now, why did we know it's in between? Because it said X 2.5. Definitely you would have moved 2.5 before you complete 5. So definitely it's even halfway. So let's call this point 2.5. Then Y is also 0. So let's say they're asking us to calculate the electric field intensity at this point. Now, the electric field intensity at this point will not just be a singular electric field intensity. Why? Because electric field intensity is the force per unit positive test charge. Electric field intensity is the force per unit positive test charge. Let's drop that positive test charge here and call it Q. So we have Q1, we have Q, we have Q2. So now you have Q at this point. So now I've redrawn it so that we can properly analyze. So the first electric field intensity will be calculated. We'll call that one E1, which is relative to these two, the positive test charge and the Q1. The second electric field intensity will be calculated. We'll call that one E2, which is relative to these two, the positive test charge and Q2. So E1, definitely the formula for electric field intensity remains force per unit positive test charge, which is Q, right? Now, if it is the force per unit positive test charge, the force here is existing between these two, right? That's Q and Q1. So the force formula is K Q1 Q, right? Over R squared. That's distance between the two of them. Then we now have all over what? Q. The force over what? Q. So this Q is positive test charge to cancel this particular one. So we are left with this. So K Q1 over what? R squared as the formula for E1 we're going to use. So Q is 9 times 10 raised to the power 9 times this Q1, definitely 25 times 10 raised to the power minus 9. This R in this case now is what? The distance between the positive test charge and what? Q1. That's definitely what? 2.5. So 2.5 square. Using your calculator well, this will result in 36 Newton per coulomb. Why is it Newton per coulomb? Force per unit what? Positive test charge. So we settled E1. E2 now, in the case of E2, like I said, that will be relative to these two now. So E2 is going to be same force per unit what? Positive test charge. But this time around, the force is going to be K, Q what? Q2Q all over what? R square all over what? Q. So now Q goes with Q. You know we are dealing with relative with respect to these two. So now we are left with K Q2 over what? R square as our formula. So using that formula now, K is what? 9 times 10 raised to power what? 9 times Q2 minus 25 times 10 raised to power minus 9. Let's quickly make a correction here. Modular. Assuming we have placed our modular sign, while we are cancelling, we would have cancelled this. Good and fine, right? So we'll be left with the modular what? Form. So luckily for us, this one was positive, so there was no influence. So where we remembered now was the case of a negative. Put the modular sign back. So you have the modular sign left here. So definitely this negative will not exist. I think I did something like this in my last class. So you now have 25 properly. 25 over R square. The distance between these two, if here to here is 2.5 and the full distance is 5, definitely here to here will also be what? 2.5. So you have 2.5 on this side, 2.5 on this case, and also 2.5 in this side. So at the end of the day, you'll now be having over 2.5 squared. Using your calculator well will result in also another 36 Newton per coulomb. That one settles it. So no negative. So having this now, since we use the correct formula, modular form. So now, as we said before, the electric field, you know, just like the question said, let's go back. The electric field intensity at the point this. So the electric field, total electric field intensity will be a sum of the two electric field intensity. So we have E as what? E1 plus E2. So definitely that's going to be 36 plus 36, and that's going to result in 72 Newton per coulomb. But if you want to describe this electric field intensity, just like the way I explained in my last class, now this is a positive test charge, right? And this is the point at which they ask us to determine the electric field intensity. You have a positive charge here too. Using Coulomb's first law, definitely these two will not attract. This will move, this positive test charge will move away from this guy because they are both what? Positive. So this, the electric field intensity will move away from what? The first charge, that's Q1. Why? Since this Q2 is negative, remember, see Q2 as negative, the electric field intensity will move towards it because the electric field intensity is always considered with respect to a what? A positive what? Test charge. So it will move away from any other positive charge and move towards a negative charge. So the electric field intensity is 72 Newton per coulomb, and its direction is away from Q1, which is the 25 times 10 raised to power minus 9 coulomb charge, and towards Q2, which is the minus 25 times 10 raised to power minus 9 coulomb. Thank you.